Hey guys, this is Miss Bufford, and in this video we're going to talk about oxidation numbers and identifying oxidation and reduction. So your learning goals are to be able to determine the oxidation number of elements in an oxidation-reduction reaction and identify the species being oxidized or reduced. We will also identify the oxidizing agent and the reducing agent. So what is an oxidation number? Sometimes, all the time, chemical equations show us how atoms rearrange themselves relative to one another to form new substances, but they don't always show, or they don't ever show, the movement of electrons within that reaction. One way to visualize this or keep track of the movement of electrons in a chemical reaction is to assign oxidation numbers to each element or ion. An oxidation number is a hypothetical number that's assigned to an atom or ion using a set of rules, and it allows us to see what's happening with the electrons in that chemical reaction. So an element whose oxidation number changes from the reactant side of an equation to the product side are the elements that are involved in the oxidation or reduction that's taking place. When an element loses electrons, it is oxidized, and when an element gains electrons, it is reduced. So this information right here is really important, and we're going to come back to it. We'll talk about it some more here in just a little bit. Anyways, when we assign oxidation numbers using this set of rules, the one that we're going to talk about on the next slide, we're grouping electrons with the most electronegative elements in each substance. So we're basically assuming that all bonds are 100% ionic. And of course, we know this is not true, but when we think about electrons this way, it helps us to really see where these electrons are moving and why they're moving where they're moving. All right, so let's go ahead and take a look at the rules. So there are 10 rules that we're going to use to assign oxidation numbers. The first one is that an element by itself is equal to 0. It has an oxidation state of 0. Any element from group 1A will always have an oxidation state of +1. Elements from group 2A will always have an oxidation state of +2. Halogens usually have a -1 oxidation state, but they can be positive when they're with oxygen. Monatomic ions will have an oxidation state equal to that ion's charge. And this is really for elements that we don't have a very specific rule for. And we'll do an example here in just a minute that demonstrates that. Rule number 6 is hydrogen is a +1 oxidation state when it's with nonmetals, and it will be a -1 with metals. Oxygen usually has an oxidation state of -2, but it can be -1 in peroxides or superoxides. In this class, we're only really going to see oxygen as -2. We're not really going to see many peroxides. Fluorine is always -1. And rule number 9 says that the sum of all of the oxidation numbers in a neutral compound, meaning a compound that has no charge, will equal 0. And rule number 10 says that the sum of all the oxidation numbers in a polyatomic ion will equal the ion's charge. And so if I add up all those oxidation numbers for a neutral compound, my oxidation the sum of all the oxidation states should equal 0, and then for the polyatomic ion, it has to equal the ion's charge. All right, so let's go ahead and do some examples. I'm going to take a look at chlorine first, right here. This is Cl2. Remember, chlorine is a diatomic element. They exist, paired up together in their pure state in nature. And this is chlorine in its elemental form, so it's going to have an oxidation state of 0. All right, so now let's go ahead and take a look at this oxygen right here. Oxygen, in this case, has a -2 charge. So although this oxygen is alone, it's by itself, it is not in its elemental state. It's an ion. And so the oxidation state here for oxygen will be -2. And we could look at the rule for oxygen for that, or we could think about the rules for monatomic ions. Either way, it's -2. All right, let's take a look at water. Oxygen, the rule for oxygen is -2. And the rule for hydrogen when it's with a nonmetal is +1. And just to double check to make sure that we've got everything right, this is a neutral compound. It has no charge on it. And so what I'm going to do is I'm going to add up all of the oxidation numbers from each atom in this compound. So all of the oxygens, there's only one oxygen. Each oxygen contributes a -2 charge. And then hydrogen, each hydrogen contributes a +1 charge, and there are 2 of those, so I have a total of +2 from the hydrogen. And so that is a true statement. 2 minus 2 equals 0. All right, so let's go ahead and do ammonia. I have a rule for hydrogen. The rule for hydrogen when it's with nonmetals is that it is +1. And in order for this to equal 0, because it's a neutral compound, I have 3 hydrogens for a total of 3 positive charges. In order for that to equal 0, nitrogen would have to be -3. All right, so nitrogen is -3. All right, let's go ahead and do cyanide. This is a polyatomic ion, so the sum of all of the oxidation numbers from carbon and nitrogen has to equal -1 because that is the charge on that polyatomic ion. And there is no specific rule for either carbon or nitrogen. And so I'm going to look at my periodic table really quick. And I know that nitrogen is in this family right here. And this family tends to form -3 ions. So nitrogen in this case is going to be it's going to have an oxidation state of -3. And if that's the case, there's only one nitrogen. And so carbon would need to be a +2 in order for this to be a true statement. So carbon in this case would be +2. All right. Calcium hydride. I have a rule for both of these. Calcium is a group 2 metal, so it will have a +2 oxidation state. And hydrogen in this case is with a metal, so it's going to have a -1 oxidation state. So let's go ahead and make sure that this equals 0 because that's a neutral compound. I have a +2, and then coming from my hydrogens, I have a total of -2. And so that right there, 2 minus 2 equals 0 is a correct statement, true statement. All right, so let's do silicon dioxide. I've got oxygen here. There's a rule for oxygen that's -2. And I'm not sure about silicone, so let's go ahead and we'll set this equal to 0. I have a total of 2 oxygens. Each one of those has a -2 oxidation number. So that's a total of -4 coming from all the oxygens. So silicon would have to be +4 in order for that to balance out. All right. Manganese oxide, so oxygen, -2. And then again, I'm not sure about manganese, so I'm going to go ahead and set this equal to 0. There are 2 oxygens, and each oxygen contributes a -2 to the oxidation number for a total of -4. And so in order to balance that out, manganese would also have to be +4. All right. And remember that if I'm asking you for the oxidation number of an element, I want the numbers that I'm writing down here above each of these elements in each formula as the oxidation number. So you don't want to give me the collective amount. Don't tell me what the total amount of oxidation number is or charge is for an element in a compound. I want the oxidation state of each individual atom. All right. All right, so let's go ahead and go down to nitrate. Nitrate here, we've got oxygen and nitrogen. It is a polyatomic ion, so we're going to go ahead and set that equal to -1 because that's the charge. Oxygen is going to have a -2 oxidation state. There's a total of 3 oxygens, so that's going to give us a total of -6 charges from the oxygen. And then nitrogen is going to have to counterbalance that in order for this to equal -1. And so we're going to have to add a +5 to that. So nitrogen is going to be +5. All right, next compound. This is called sulfuric acid, H2SO4. There is a rule for hydrogen and a rule for oxygen. My rule for hydrogen is that when it's with nonmetals, it is +1. My rule for oxygen is that it's -2. And I'm going to go ahead and set this equal to 0 because it's a neutral compound. And so the total amount of negative charge from oxygen is going to be -8. And the total amount of positive charge from the hydrogens in here is going to be +2. So I need to figure out what I'm going to put in here in order to make this a true statement. It has to equal 0, so this is going to have to be +6 for sulfur. All right, so let's do this next iron compound. We've got iron 2 oxide. Oxygen is going to have a -2 oxidation state here. And because there's only one oxygen and only one iron, I can easily see that iron is going to have to be +2. All right, so that one was a quick and easy one. All right, the next one, again, I have an iron oxide compound. This is iron 3 oxide. I'm going to go ahead and set this equal to 0 because it's a neutral compound. I have a rule for oxygen. Oxygen is -2. This is going to give us a total of -6 charges from the oxygen. And so the total amount of charge from iron is going to have to be +6. But there's a twist with this one. I have 2 irons here. And so I have to distribute this positive charge right here between the 2 iron atoms. So I really have to divide it by 2. And that means that each individual iron atom is going to have an oxidation state of +3. All right, so I hope these were helpful. What we're going to do is we're going to take the information that we learned on this slide, the skills that we learned, and then we're going to apply them to a chemical equation on this slide. And so now we've reached the point where we're ready to identify oxidation and reduction. So I've broken this down into some steps. The first thing that we want to do is we want to go through this chemical equation and we want to assign oxidation numbers to all of our elements. So let's go ahead and do that. This first compound down here is potassium permanganate. I have a rule for potassium, which is +1 because it's a group 1 metal. And a rule for oxygen, that's going to be -2. And again, this is a neutral compound, so I'm going to set it equal to 0. I'm going to have a total of -8 coming from all 4 oxygens and a total of +1 from potassium, which means that manganese is going to have to be +7 in order for that to be a true statement right here. All right, I have a rule for hydrogen and chlorine. Hydrogen is +1 because it's with a nonmetal, and chlorine is -1 because it is a halogen. All right, next compound. Chlorine again is a halogen, so it's going to be -1. I'm going to set this equal to 0. There are a total of 2 negative charges coming from chlorine, and to balance that out, manganese would have to be +2. All right, chlorine here is in its elemental state, so I'm going to put a 0 above that. And next we have the water molecule. So hydrogen here is with a nonmetal, so it's going to be +1. And oxygen is -2, and this balances out because we've got 2 hydrogens for a total of +2. -2 equals 0. All right, and then the last compound, potassium. Potassium is going to be +1, and chlorine is going to be -1 because it is a halogen. All right, so now we've gone through and we've assigned all of our oxidation numbers here. And step 2 says to find the elements whose oxidation numbers changed when the products of the reaction were formed. So what we're doing is we're looking on the reactant side and on the product side, and we're looking to see which 2 elements had oxidation numbers that changed. And the first one that I see is manganese. Manganese went from a +7 to a +2. And the second one is chlorine. So chlorine went from a -1 to a 0. And we do still have this -1 chlorine down here, but that's not part of this redox interaction, so we're just going to, that one is a spectator. All right, so the next step is we're going to use the acronym OIL-RIG, which means oxidation is loss of electrons, reduction is gain of electrons, and this can be very helpful if we're really trying to figure out what's happening with the electrons, which we eventually, we'll be figuring out what happens with the electrons. But I think the easiest way to identify what's being oxidized and what's being reduced is to first identify which one is being reduced. And the way we do that is that if the charge is reduced, then it's reduction. That means if the charge goes down from the reactant side to the product side, that's your reduction. All right, so chlorine starts at -1 and it goes to 0, and that is actually considered going up. And so manganese, it starts at +7 and it goes down to +2. So that oxidation number right there is being reduced. So this is reduction. And that's because manganese went from a +7 down to a +2. All right, that means the other one is automatically oxidation. And now here's where oil rig comes in. So I want to know what's happening. Okay, I've labeled these oxidation, I've labeled it reduction, but what's actually happening here? So oxidation is loss. And so what we've just said here is that chlorine loses electrons when it's oxidized. So chlorine is losing electrons and they're transferring to manganese. Manganese is reduced, which means it's gaining electrons. And the reason we say that it's reduced because it's gaining electrons is because it's gaining negative charge and its charge is going down with every negative charge it pulls in. All right, so its charge is being reduced by pulling in all those negative electrons. All right, so this is the interaction we've just described. So chlorine is giving electrons to manganese, and when chlorine gives its electrons away to manganese, it becomes oxidized. All right. In turn, at the same time as it's giving these electrons to manganese, manganese is being reduced. So chlorine is reducing manganese, all right? But also in turn, manganese, in accepting those electrons from chlorine, is causing the oxidation of chlorine, and it's being reduced. Manganese is being reduced, but it's causing the oxidation of chlorine. And so here's where we come into identifying the oxidizing and reducing agents. If you are the agent of something, if you've ever heard the phrase agent of change, then you are causing change to happen. If something is the agent of change, it's causing something to happen. And so if we call something the oxidizing agent, it's causing oxidation to happen. If something is the reducing agent, it's causing reduction to happen. All right, and so chlorine, when it gives away its electrons, is causing the reduction of manganese. And so when we go over here to label our oxidizing and reducing agents, they're always going to be on the reactant side of the equation, right? They're always going to be on this side. And if I'm looking for my oxidizing agent, then manganese is causing the oxidation of chlorine when it pulls in that electron. So this whole compound right here is going to be my oxidizing agent. All right. And then chlorine is causing the reduction of manganese when it gives its electron away to manganese. All right. And so this compound right here is going to be our reducing agent because it causes the reduction of manganese. All right, so the agent causes something to happen. All right, so let's go ahead and do a couple more examples. All right, so what we're going to do here is the same thing that we did on the other slide. We're just going to determine the species being oxidized and reduced. And then we're going to label the oxidizing and reducing agents in these two reactions. All right, so the first one, I've got carbon. It's in its elemental form by itself, so I'm going to put a 0 above that. Hydrogen is going to be +1. Oxygen is -2 here. So then I've got a total of -8 coming from oxygen, total of +2 coming from hydrogen, so sulfur is going to be +6. All right, oxygen here is going to be -2. That's a neutral compound. So I've got a total of -4 here. So carbon is going to have to be +4. Right, it's going to be a similar story here with this one. Oxygen is -2. It's a total of -4. So sulfur is going to have to be +4 here as well. And then, of course, water, hydrogen is +1, oxygen is -2. All right, so now what we want to do is we want to go through, we want to look for where the changes are occurring. So I can easily, quickly see that carbon is going from 0 to +4, and that sulfur is going from +6 to +4. All right, and now I want to label which one is reduction and which one is oxidation. So remember, if the charge goes down, it's reduction. And in this case, sulfur went from a +6 down to a +4. So this is going to be our reduction half of the reaction. Right, and that means this is going to be our oxidation half of the reaction. Right, and oxidation and reduction, they cannot happen separate from one another. This is a transfer of electrons. It happens, pretty much simultaneously as these electrons are being transferred. So in this case, what we've said here is that carbon is oxidized, so it's losing electrons and transferring those electrons to sulfur. All right. And now we need to identify our oxidizing agent and our reducing agent. So carbon was oxidized and sulfur was reduced. Okay, carbon, when it oxidizes and it loses that electron, causes the reduction of sulfur. So that means carbon has to be our reducing agent. Okay, and then in turn, when sulfur accepts that electron from carbon, it is causing the oxidation of carbon because it's pulling that electron away from carbon. And so this compound right here that contains that sulfur is going to be our oxidizing agent. All right, so you can see that they're opposite. If you are the element that's reduced, then the compound you started in is the oxidizing agent. And if you are the element that is oxidized, in this case carbon, then you start out in, the substance that is the reducing agent. All right. So let's go ahead and do one more example. I've got nitric acid here, so HNO3. This is going to be a +1 for the hydrogen, a -2 for oxygen. This is going to be a total of -6 +1. So nitrogen in this case is going to have to be +5. And then hydrogen here is going to be +1. Iodine is -1. Over here I've got oxygen as -2. That means this nitrogen is going to have to be +2. Iodine is going to be in its elemental form here, so it's going to be 0. And then hydrogen +1 and oxygen -2. All right, so now let's go ahead and take a look for the changes that occur. I've got nitrogen going from a +5 to a +2, and I also have iodine going from a -1 to 0. All right, now we're looking for where the changes or where the reduction has occurred. So remember, if the charge goes down, it's reduction. So nitrogen has a +5. On the reactant side, and on the product side, it goes down to +2. So this is going to be reduction. And on the other side, this is going to be oxidation. And so what we've described here is iodine giving its electrons away or transferring its electrons to nitrogen. All right, so iodine is oxidized, nitrogen is reduced. And iodine, when it transfers that electron to nitrogen, it causes the reduction of nitrogen. And so this right here, the compound that iodine started in, is going to be our reducing agent. All right, and then when nitrogen accepts that electron from iodine, it causes, in turn, the oxidation of iodine. So this nitrogen-containing compound right here, so that nitrogen is in that compound that causes the oxidation. So this is the oxidizing agent. All right, so I hope this video was helpful. If you have any questions, go ahead and write them down and we can talk about them in class. Thanks for watching Buffered Chemistry. Subscribe to my YouTube channel for more chemistry help.